The next separating technique we're going to look at is simple distillation. Again, something you should have met before in junior school. But distillation is a method that can be used to separate a solvent from a solution. Let's do a recap of our definitions again. What is a solvent? The solvent is the liquid in which the solute dissolves. And what is the solution? It's the mixture of the dissolved solute and the solvent. So for example, what we're talking about here is if we had a solution of salty water, it would be separating off the water from that. So think back to evaporation. We use that to separate a mixture of salty water. But what we did with that was we collected the solute, but the solvent evaporated off and we could not collect that. So evaporation loses the solvent essentially. So distillation can be used if we want to keep the solvent, if we want to collect it as well. So if we were using distillation to separate salty water, we could collect the solute and the solvent. And this is also a way of purifying a substance as well. So earlier on in the video we looked at mineral water being impure water with other ions and salts dissolved in it. But if I just want pure water molecules only, I can use distillation because it's only the water molecules that will come over and be collected in the flask. And we'll see that in just a second. So distillation works by a process of evaporation followed by condensation. So our water molecules are going to evaporate, be passed through into a condenser, and then condense back to form water again. You may see anti-bumping granules in your diagrams in an exam, and they're simply added to promote smooth boiling. And what we mean by that is just so that it doesn't boil out of control really vigorously and be splashing all about the place. Smooth boiling, if you add anti-bumping granules, you'll just get nice small bubbles when it is evaporating off or boiling, so that it is not boiling too vigorously. So let's have a look at the apparatus. So over on page 12 you can see the apparatus, and we'll just zoom in so that you can see it. It's all been labelled for you, so you don't need to do that. Again, hopefully this is something that you are familiar with. You can see here in our round bottom flask on the left hand side we have our solution to be separated. So say for example we were separating salty water, we would put that into our round bottom flask along with some anti-bumping granules to make sure it didn't boil too vigorously. And what we want to do is we want to heat this flask. What will happen when we heat this flask? Well, what will happen initially is that the solution will start to heat up, and once it has got hot enough, once the water molecules start to get enough energy, they will evaporate off as steam. So they will evaporate off as steam. The steam will then pass to the top of the flask, and you can see here we've got a thermometer, and the thermometer is there to measure the temperature at which the gas passes into the condenser. So the steam will pass into the condenser through the neck here. And what you can see here is that we have got something called a Liebig condenser. So that's the name of this condenser. Now what I want you to see is that we've got an inner tubing and an outer tubing. So the inner tubing is where the steam passes. But what we've got on the outside is an outer casing. And in that outer casing flows some cold water. So I'm going to put cold water in at the bottom. So it goes in at the bottom and out at the top. So the cold water flows all around the outside of the condenser, but what it's really important to notice is that the cold water along the outside of the condenser never meets that steam that is flowing through the inside of the condenser, the inner tubing. So those are two separate tubes. So almost think of a toilet roll inside a kitchen roll. So the steam is passing through the toilet roll as such, and the cold water is passing through that gap in between the toilet roll and the kitchen roll. So if we were to cut it down the middle as such and look at it face on, the steam would be passing through this inner tubing and the cold water will be running along the outside. They never mix. Okay, so the point of the condenser is to cool down the steam so that it will cool down and condense from a gas into a liquid. Remember, condensation is the change of state from a gas back to a liquid. So we want this condenser to be nice and cold so that the steam cools down and changes back into a liquid. And then what will happen is eventually the steam has cooled down, it's formed water, and the water passes through into a beaker or whatever flask we've used to collect it. Now, the general name given to the liquid collected in this process is called the distillate. So think back to filtration. The liquid that passed through the filter paper was called the filtrate. This is distillation, and so the liquid that is carried through is called the distillate. And let's not forget about what else was in our solution. We had salt dissolved in our solution, so what has happened to it? Well, it has got left behind in the flask because at this temperature the salt will not even melt, never mind evaporate as well. So the water will evaporate, pass through the condenser and so on, but the salt particles will be left behind. So let's run that through that quickly again. So we heat the solution, the water will evaporate. The temperature on the thermometer as the steam is passing into the condenser will read 100 degrees C as the steam is passing it, because that is the boiling point of water. So that thermometer is there to tell us the boiling point of the gas that is separating off at that point. So the steam then passes into the condenser. The condenser is cooled down by this outer jacket of cold water in the Liebig condenser. So the steam is then cooled down, and so it condenses to form water again, and it passes into the beaker and is collected as what we call the distillate. So again, I don't have a video of me carrying this out, so what I would like you to do is to watch the free science lessons video on distillation, which will explain this process. So pause the video now and then watch that. What I'm then going to do is I am going to put up some steps, but they're not going to be in the correct order. So I'm going to put up the steps of distillation. They're not in the correct order. So what I want you to do is to write them into your notes in the correct order. So here are the 6 steps that need written into your notes in the distillation steps. And they are not in the correct order, so you need to put them in the correct order and write them in. So you'll need to pause the video so that the steps remain on the screen and you can write them into your notes. So just to give you a head start, the first step will be the solution is heated. So what happens after the solution is heated? So try to put these in order in your notes. And then I'll go through them to make sure you've got them in the correct order. So pause the video now and put those steps in the correct order in your notes. So as already discussed, the first step is the solution is heated. What happens after the solution is heated? Well, when the solution is heated, the water evaporates and forms steam, and the salt particles stay behind. What then happens after that? So once we form the steam, it will pass into the condenser, and the temperature on the thermometer will read the boiling point of that particular component of your mixture that is separating off. Once the steam is in the condenser, what happens next? Well, the cold water flowing around the outside of the condenser will cool the steam. What then happens next? At this stage, the steam, as it cools down, it will condense to form pure water, so it changes back from a gas into a liquid again. And then the water will run into the container that you're collecting it in. So make sure those are in the correct step and change any that you need to. And the final question on this page says, what is the name of the liquid collected during distillation? And that is called the distillate. So the general term for the liquid that is collected in distillation is called the distillate. So this particular type of simple distillation is used to separate a solvent from a solution. It can also be used to separate 2 liquids that do mix, as long as they have a very different boiling point. But there is a slightly different method to do that called fractional distillation, which we will look at now. So fractional distillation is a better method for separating two or more miscible liquids. That's liquids that do mix. So for example, we can use it to separate water and alcohol, and we can use it to separate crude oil, which we will see in more detail next year. The key thing with this, and the key thing that they would ask you on this, is how does fractional distillation work? On what principle does it work? It works that each liquid will have a different boiling point. And that means that they will separate off at different temperatures. So the liquid with the lower boiling point will evaporate first. It then passes into the condenser, condenses, and is collected. So it evaporates first, condenses, and is collected. And then what we do is when we see the temperature start to rise again, we can use a separate container to collect the liquid with the higher boiling point. It will separate off afterwards. And each liquid that is collected is what we call a fraction. Think of it as just a fraction of your initial mixture. And that's what we call the different liquids that are collected, the different distillates that are collected at each different temperature. So if we were separating water and ethanol, which is a type of alcohol, the two boiling points of ethanol and water are, for ethanol, it is 79 degrees C, and for water it's 100 degrees C. So which of those is going to separate off first? Well, of course it's going to be the ethanol. So when the mixture is heated, the ethanol will evaporate off first at 79 degrees C. So you'll see the temperature in the thermometer is 79 degrees C. It will evaporate off, pass into the condenser, it will be cooled down, it will condense, and it will be collected in a container. And then what will happen is we can switch containers. Once all the ethanol has been separated off, the temperature will start to rise again on the thermometer. And once it has reached 100 degrees C, the water will be evaporating, will be passing through into the condenser, and it can be collected in a separate container once it has condensed and formed a liquid again. So it is always the liquid with the lower boiling point that will separate off first. And if you're using this to separate 3 or 4 or 5 different miscible liquids, then it will go in order of boiling point as the temperature rises. So fractional distillation only works if you have liquids that have very different boiling points. If the boiling points are too close, say for example ethanol had a boiling point of 99 degrees C, we probably couldn't use this because the boiling points are too close. So it works on the principle that they have different boiling points. That's really important. You can have a read through this next paragraph, which just talks about how ethanol is collected at 79 degrees C. The temperature will remain at 79 degrees C until the ethanol is separated off. That's just based on the principle that we looked earlier in this topic, that substances stay at the same temperature when they are changing state, even though they're absorbing more heat. And then once that's all separated off, the thermometer will start to rise again, and then we should switch our container to collect the water, which will evaporate off at 100 degrees C. So just have a wee read through that. So what we're going to look at now is the apparatus for fractional distillation, which is exactly the same as simple distillation, because essentially this is basically the same process, but there's one additional piece of apparatus within the whole collection of apparatus, which is called a fractionating column. So a fractionating column is added into the apparatus, and it just allows for better separation of liquids. If you have got a cheeky little bit of water that has evaporated off with the ethanol, it will condense again in the glass beads and run back into the flask, and it just makes sure none of the water molecules evaporate off with the ethanol first. And there's just a quick little note here, the ethanol is flammable, so it's probably not a good idea to heat it with a Bunsen burner. What you should do is heat it using an electric heating mantle or a water bath, because a Bunsen burner could cause the ethanol to catch fire, which would obviously be dangerous. So here is your apparatus for fractional distillation, and you can see that the only addition is this fractionating column, which is filled with glass beads, so that if any of the liquid with the higher boiling point starts to separate off with the other liquid, then it will collect in the glass beads, it will condense and fall back into the flask, and it just improves the purity. You might want to add the word heat to this diagram, just to make sure you know that you heat that. So again, this works by a process of evaporation followed by condensation. So the liquid with the lower boiling point evaporates and then condenses and is collected. Then the liquid with the next boiling point will evaporate, then condense. Then if we've got more than 2 liquids, again the next liquid will evaporate and condense, and so on until all the different liquids are collected in their separate fractions. So remember that simple distillation and fractional distillation work by a process of evaporation followed by condensation. And fractional distillation is used to separate 2 or more liquids with different boiling points. Remember, they must have different boiling points. And again, what I would like you to do is to watch the Free Science Lessons YouTube video on fractional distillation to make sure you understand this process. So pause the video now and watch that. Our next and final separating technique that we're going to look at is chromatography. And chromatography is a method of separating mixtures of soluble substances in a solution. So for example, separating the mixtures in inks, dyes and colouring agents in food. So in chromatography, there are 2 phases. There's a stationary phase and a mobile phase. And there's different types of chromatography, but we're just looking at paper chromatography. And this will then explain the joke on the front of your booklet. The stationary phase in paper chromatography is the paper. And that word stationary as in does not move. And the other phase is called the mobile phase, which is essentially the phase that does move. And that is the solvent. And in our case, in the example we're going to look at in a second, and in most cases the solvent is water. So the stationary phase does not move, while the mobile phase does move. And within our mixture, each substance within the mixture moves up the paper at a different rate, and that depends on the relative attraction to the paper and the solvent. It depends which it is more soluble. So substances which have a stronger attraction to the solvent, i.e. the water that is bringing up and separating the mixture up the paper, they're more soluble in it and they will move more quickly and travel further up the paper. Substances that have a stronger attraction to the paper will move more slowly and they only travel a short distance up the paper. So when they separate out, the ones that are more attracted to the paper will be lower down on your chromatogram. The substances that have a stronger attraction to the solvent will be further up your chromatogram, and it's important that you know that. So a lot of key information on the page here. So they could ask you as a 1-mark question, what is the stationary phase in paper chromatography? And it's simply paper. And they might ask, what is the mobile phase in paper chromatography? And that will be the solvent, and quite often that is water. And again, they could ask you which of the substances is more soluble in the solvent, and that's the one that is further up the page. Or they could ask you which is more attracted to the paper or the stationary phase, and that's the one that is lower down in the chromatogram. But we'll see that when we see a diagram of the chromatogram. Over on page 15 then you have the method of chromatography, and this might look a bit scary, but you do need to know this method. It has come up as questions over the past few past papers, so it is really important that you learn this. Now, you don't need to learn this word for word. You need to work on summarising this method into a format that you can learn off by heart. But I'm going to show you this and show how you do it, which hopefully will help you learn this method. What I want to look at is point 10 here, which is calculating the RF value. And we will come back to this after you watch the videos of me carrying this out. But the RF value is the distance travelled by the spot divided by the distance travelled by the solvent. We will come back to this, but it's important that you know that RF values have no units. So RF values have no units, because you will be doing distance divided by distance. So say for example you measure it in centimetres, your centimetres will cancel out on the top part and the bottom part of your fraction. So they're written as a decimal, usually to 2 decimal places. And they should always be less than 1, because your solvent will always travel further than your spot. Your spot should never travel further than the solvent. In fact, it can't travel further than the solvent. And that's why it's really important to mark your solvent front. And I'll discuss that in the video. So what I want to do here is show you how to carry out chromatography just by simply separating the inks in a couple of different markers. So you can see I've got my markers up here, and I've got my piece of chromatography and a ruler and a pencil. So according to the method, the first thing you need to do is to draw what you call the baseline. Now this must be drawn in pencil. Because if you drew it in pen is made up of different inks which would then separate out. So I want to draw my baseline about 1 to 2 centimetres from the bottom. I don't want to draw it too high because then it will be a long time before the water reaches my spots, but I also don't want to draw it too low because this line must be above the water level when I go to put it in my beaker. What I'm then going to do is I'm going to mark with a pencil again the X's where I am going to put my spots. So I'm going to put X's where I'm going to put my spots of my marker. Okay, then what I want to do is get my first marker, and I'm going to just put a small spot in the centre of that X. Just doing a couple of spots just to make sure the ink has transferred, and I'm going to put that at the centre of the X. So I'm going to do blue, and I'm also going to do grey. So again, on the centre of this spot, I'm going to put a few dabs of my grey marker. Now if you had a solution, you might use what we call a capillary tube and just add a few spots into the centre of your X. Then what we want to do is put it into our beaker. So you can see here I've got a beaker of water, and again it's really important that the water level does not go above your baseline. If it does, then you will need to start again, because the dyes will just dissolve in the water and run into the water rather than the water carrying the spots up the page. So what I've done is, you can see here I have wrapped my piece of chromatography paper around a pencil just so that I can suspend it in. I might need to lower it down a wee bit, but we'll check in a second. So all we need to do is have the water. All we need to do is have the water below the baseline, but make sure that it's reaching the chromatography paper, and you can see that it does here. Now hopefully you can see this starting to work, and if you look very, very closely at the edge here, you can see the water level starting to rise, and as it rises, the ink of the pen is dissolving in the water, and it is carrying up the page. So you can see gradually the inks of the pen are going to separate out. Now unfortunately with these types of pens we don't tend to see just nice clear cut spots, but you will start to see the colours separate out. So what we're going to do is leave that to separate out. I'm going to take a time-lapse video just to speed this up a little bit. But essentially what you're doing now is letting your water run until the water reaches nearly the top of the page, but we don't want it to totally reach the top of the page. And that's the advantage of using a pencil as well, so that it doesn't reach the very edge of the page. So remember, this video has been sped up, but you can see the water level rising up the piece of chromatography paper, and you can see the different coloured inks within the pen separating out. So chromatography is separating out the different soluble substances within the ink. So the different colours are soluble, and the water is bringing them up the piece of chromatography paper depending on their solubility. So now that the different inks have separated out, what I want to do is I want to take it out of my water. Just let the excess drip off there. And I'm setting it down onto my desk. And what I want to do is to mark the level where the water got to. Now the water will start to, if you still have a lot of water, it will keep travelling up a little bit to some extent. But we mark where the water has got to, the solvent has got to. That's really, really important for when we calculate what we call our RF values. So move my beaker out of the way there, and what I want to do next is to just draw a straight line across. And that's the level to which my water got to. So this is what we call the solvent front. That's essentially how far the solvent travelled. And what you can see here is that this was originally my blue, and this was originally my grey. And you can write those on beforehand if you want to try and remember those. And what you can see is that my grey ink has separated out. You can see there's like a yellow spot here, there's like a brown here, and there's quite a bright blue up here. So you can see that grey ink is made up of yellow, brown and blue. And as I said, we don't get those nice clear cut spots, but you can see that it's separated out into the individual colours that the ink is made up of. So you can see that grey is a mixture of yellow, brown and blue ink. But look at my blue pen. Has it separated out into different colours? And you may see a streak of it here, but essentially that's just the bit that's clung to the paper. But you can see that it hasn't separated out into different colours. I'd say the main spot is here, but you can see that it is just blue. And so we can see that blue ink is only made up of one colour of ink, and that is blue. So it is what we will call a pure ink. It is only made up of one colour, whereas grey is a mixture of three. Now it's important that you mark the solvent front when you take it out, because this water will dry and then it's impossible to see where the water got to. And what we can do is calculate our RF values, and that's simply a comparison of how far has my spot got to in comparison to how far the solvent front has got to. And we will look through that now. So over on page 16 you have a couple of diagrams which represent diagrams for the different steps within the chromatography process. So you can see preparing your chromatogram, running your chromatogram in your solvent, and then what you're left with at the end, which is called our final chromatogram. You can see your spots separated out and your solvent front marked. And what I want to do is take you through how we calculate RF values. So I'm going to add some notes to this final diagram here. So I'm going to call this lower spot, spot 1, and I'm going to call this second one spot 2. Okay, and we calculate a separate RF value for each of the spots because you can see one has travelled further than the other. So we need to remember our equation for calculating the RF value, and it has been asked in exams to just simply quote the equation for calculating RF values, so it's important that you know it, and it's on the previous page in your booklet. And it's a very simple calculation that the RF value is the distance travelled by the spot over the distance travelled by the solvent. And in an exam, if you were asked to quote the equation, that's what you would need to write. If you were just asked to work it out, what you're thinking of is spot divided by solvent, and you need to remember that it should always be less than 1, and it will have no units, as we will see below. So let's calculate our RF value for spot 1 and for spot 2. So we need some values in order to do this, and in the exam you may be asked to work out the distances using a ruler, or they might give you some values. I'm just going to give you some values. It's not to scale, but it's just to make our calculation a little bit easier. So what we'll need first of all is the distance travelled by our spots, and also the distance travelled by the solvent. These are always measured from our pencil line at the bottom, which is sometimes called our baseline. So I'll write that below our pencil line. So it's always measured from the baseline. So from the baseline to the spot, and it's the centre of the spot that we use, and from the baseline to the solvent front. So let's do the solvent front first of all. And I would like you to mark on your diagram that the solvent has travelled 4 centimetres. So the difference between your baseline and your solvent front is 4 centimetres. Okay, that might not be to scale within your notes, but that's what we're going to write down for this. If you want to, you can measure your exact values using a ruler and calculate them that way. But just to give you an idea of how you calculate this. So that's the first value we need, and we'll use that for both our calculations. We also then need to know how far spot 1 has travelled, and we always go to the centre of the spot. So what I want you to write in is that spot 1 has travelled 1 centimetre. Okay, again, that might not be exact, it might not be to scale, but let's just write that in for our calculation. So let's look at our RF value. Our RF value is the distance travelled by the spot, which in this case is 1 centimetre, divided by the distance travelled by the solvent, which in this case is 4 centimetres. You can see now why there's no units, those centimetres cancel out. 1 divided by 4 is 0.25. Remember, RF values are written as decimals and they're written to 2 decimal places, so that works out well for this. But if you get a big long decimal with lots of decimal places, then just round it off to 2 decimal places. So that's for spot 1. And then we need to do it for spot 2 as well. And again, we measure from the centre of the spot down to the baseline. So it's always measured from baseline because, think about it, that's where the spot started. And that's where the water started to travel up and bring the spot with it. So I want you to mark on that spot 2 has travelled 3 centimetres. So let's work out the RF value for spot 2. So RF, according to our equation, is the distance travelled by the spot, which is 3 centimetres, divided by the distance travelled by the solvent, which is 4 centimetres. Again, your centimetres cancel out, so I have no units. 3 over 4 is 3/4, which is the same as 0.75. Use your calculator to get that as a decimal. And again, there is no unit for this. You can see both of our values are less than 1, which shows we've done this correctly. Because again, your spot will never travel further than your solvent. So let's have a quick think about what we can interpret from these values, because remember we said on the previous page or a couple of pages ago that the RF value gives us an indication of how soluble our different substances are in our solvent, or whether it's more attracted to the paper. So which do you think is more attracted to the paper? Well, in this case, it's going to be spot 1. So this is more attracted to the paper. And the paper is our stationary phase. So spot 1 is more attracted to the paper. How can I tell that? Well, because it has travelled a smaller distance up the paper. It hasn't travelled as far up the paper. What else can we see from this chromatogram? Well, we can see that spot 2 is more soluble in the solvent. How can I tell that? Because it has travelled further up the paper. So spot 2 is more soluble in the mobile phase, which is our solvent, which in this case was water. How can I tell that? By simply looking at the diagram. Well, I can tell that because it's travelled further up the paper, and also it has the higher RF value. So the spot with the higher RF value will be more soluble in the mobile phase, which is the solvent. So from this diagram we can interpret a lot by how far the different spots have travelled up the paper. And we can also tell from this diagram that the spot we have used in this, the substance we've used in this case, is not a pure substance. The fact that there's 2 spots means that this is not pure. And we can see that in the diagram down below at the bottom of page 16. We can actually use one piece of paper as long as it's wide enough to compare different substances, and we did that with the markers when I showed you in the videos. So say for example we know what dye 1, 2, 3 and 4 are, and then we have an unknown substance. So we can use chromatography to identify the dyes or the components within an unknown mixture if I compare them against components that or substances that I do know. So you can see from this chromatogram that dye 1, 2, 3 and 4 are all pure substances because they produce only one spot on the chromatogram. Whereas our unknown is impure. It is a mixture because it has multiple spots. You can see here it has 2 spots, so it must be a mixture of multiple dyes. So if it has more than one spot, then it is a mixture. So how can I tell from this chromatogram which dyes my unknown mixture contains? Well, I can compare it to the other spots from my dye 1, 2, 3 and 4. Because the spots will have the same RF value if they have been run in the same solvent, and given that this has all been done on the one piece of chromatography paper, it must have been done in the same solvent. So certain substances will have the same RF values in the same solvent, in a given solvent. So even if I run the solvent up further, it will give me that same fraction value, that same RF value. So you can see by comparison that this spot matches up with this spot. Those spots are going to have the same RF value because they have travelled the same distance up my piece of chromatography paper. So if I took the RF value, which remember is the distance travelled by the spot divided by the distance travelled by the solvent front, you can see this is going to give me the same value. So if it's in line with one of the other spots, then that shows it contains that particular component. So you can tell that it contains dye 4. And if we look at the other spot down at the bottom and try and match that up, we can see that it also contains dye 3. So you can see that it contains dye 3 and dye 4 by comparing the spots. And if you want to be totally accurate, you could calculate the RF values of each and see which match up. But again, just by looking at the chromatogram, you can see that it contains dye 3 and 4 because it has matching spots, and that's all based on the principle that a certain substance will have the same RF value in a given solvent. So in that way, if we are trying to identify what the substance is, we can run a chromatogram, calculate the RF value and compare it to a database of known RF values. If that RF value has been measured before and has been recorded on a database, then we can actually work out what the substance is, as long as we know the particular solvent and we know the RF value. But different substances will have different RF values in different solvents. So if I have a particular substance and I use the solvent water, it will have a particular RF value, but then if I do it again in the solvent ethanol, it might have a different RF value. So you just need to be careful about what solvent you have used. So what I would recommend you doing, particularly to talk about that or to understand that idea of RF values and comparing it to known values to identify substances, what I'd like you to do now is pause this video and go and watch the free science lessons video on chromatography as well, because that really goes through the process of the method of chromatography, but then also how you calculate RF values and how you compare that to known values to identify substances. Page 17 you can just ignore. This is what we would use to stick in our chromatogram if we were doing it in class, but you can just ignore this, or what you can do is draw out your own chromatogram and calculate the RF values if you wish. So you'll be glad to know that's us at the end of our separating techniques section of this topic, and that's a massive chunk of this topic. There's just a small little bit to go. So what I want you to do now is to summarise your methods of separation. You might find this table helpful, but what I'd also like you to do is to create a mind map that summarises these methods of separation. Let me start that off with you now. So in the centre you're going to have separating techniques. Then for each method of separation of mixtures, I want you to write the name of the separating technique, the type of mixture it's used to separate, and an example of a mixture that you could use this method to separate. And if you want, you can draw your apparatus diagrams in, or include a summary of the method, say for example for distillation or for filtration or chromatography or whatever that may be. So you can add as much detail to this mind map as you want to try and learn off the details of these separating techniques, but those are the 3 things I absolutely want on this mind map. So let's take the first one, which was filtration. Next thing I want is what type of mixture that's used to separate. It's used to separate an insoluble solid from a liquid. That insoluble solid is really important. And then an example of a type of mixture that we could use this filtration method to separate. And we can use it to separate sand and water, because sand is an insoluble in water. So I want you to do this for the remaining separating techniques for evaporation, crystallization, separating, funnel, simple distillation, fractional distillation, and chromatography. And again, you could add diagrams to this of your apparatus or summary of the methods as well. But for each technique, the basic information that I want is the name, the type of mixture, and an example. So pause the video now and do that so that you process all that information. Make sure you understand what type of mixture it's used to separate before completing the next task. So at the bottom of page 18, you have a few questions which ask you to choose the method of separating technique that you would use to separate these particular mixtures. And that's why it's really important to summarise that information in your own format first, so that you've processed all that information, so you understand what method is used for what type of mixture. Because as we said at the very start of this section, the method of separating technique that we use depends on the properties of the mixture. And that's what hopefully you got across in your mind map, but also you have summarised in the table above. So use the table above to help you as well, or flick back in your notes, or use your mind map to help you as well. So you can write the answers to this on the page, I don't mind, or you can do it on a spare piece of paper if you think you don't have room. So all your separating techniques are mentioned above, and all you need to do is choose which method. So let's look at the first example. It says to separate the dyes in red food colouring. So you might want to think, well, what type of mixture is this first of all? Well, as the question suggests, food colouring contains multiple dyes, and those dyes will all be soluble in the solution of the food colouring. So the type of mixture here is multiple solutes or soluble substances in a solution. What do we use to separate that? We use chromatography to separate that. So you don't necessarily have to write down the type of mixture, but it helps you to process, well, what method would I choose? So think about what type of mixture this is, and think about what then method you would choose. So pause the video now, try this for yourself, try to identify the type of separating technique that we would use, and then I'll run you through the answers. So let's check through those now. So thinking first of all about our type of mixture. So here we want to separate salt from salt solution. Now we know that salt is soluble, and so this will all be one solution, so we can't use filtration. And it's important here that we know that we only want to collect the salt, so it doesn't matter if we lose the water. So for this we would use evaporation. Number 3 then, we want to separate the water from the salt solution. So again, we have got a soluble solute dissolved in a solution, but this time I can't use evaporation because it would lose the water. So if I want to collect the water, I would use simple distillation, and that will allow me to collect the water. So if we heat it, the water will evaporate, it will pass through the condenser, condense to form water again, and we can collect it. If you've just written distillation, that is fine. Number 4 is to separate oil and water. Well, let's think about what type of mixture this is. Oil and water are immiscible. They are liquids that do not mix. And so what do I use to separate them? A separating funnel. Number 5 then, it says to produce crystals of copper sulphate from a copper sulphate solution. So again, you're thinking you're getting a solute here from a solution. So I could use evaporation, but the question specifies I want crystals. And so what method might I use? It's slightly different. We use crystallization, which is that like slower method of evaporation to give us nice big crystals rather than just a powdered solute. So crystallization is your answer. Number 6 then is to separate a miscible mixture of gin and tonic water. So both are liquids, but they are miscible liquids. They mix, so I cannot use separating funnel because they will both just form one layer. They will mix together. And so what I want to use here is fractional distillation because that will separate, give me a good separation between my two liquids that will have different boiling points. Number 7 then is to separate water from copper sulphate solution. Again, I'm separating out a solvent from a solution, and this is a bit like number 3, how we collected the water from the salt solution. It's no different here. So what I'm using is simple distillation to allow me to heat my water, it to evaporate off, pass into the condenser, cool down and form water again, and then collect it, leaving the copper sulphate salt behind. Number 8, it says to separate insoluble copper oxide and water. Copper oxide, if you remember, is a black solid, but it's insoluble. So if I mix it with water, it will just sit at the bottom. It won't dissolve. So what can I use to separate it out? I can just simply use filtration. Number 9 then asks me to separate a miscible mixture of ethanoic acid, water and ethanol. So here we've got 3 liquids that mix together, but they will have different boiling points, so I can use fractional distillation to separate them. So hopefully from this you understand how to identify the correct technique to separate a given mixture. You could be asked to do this in your exam. What I would like you to do now is pause, take a break from the video and complete section 2 of Unit 1.9 Chemical Analysis questions, which will focus on separating techniques, and then come back to the video for the final section of this topic, which looks at the test for water and flame tests, which will be a much shorter section of the video, you'll be glad to hear.